This call is now being recorded.
Welcome everyone. This is DW301 Basic Electronics, and in this lecture we shall continue our discussion on modeling of diode. In the previous lecture we learned about the ideal diode model. It is the first approximation model, and in that model we approximated our diode as a short circuit or an open circuit on the basis of the current conditions, current and voltage conditions. So here you can understand the in the this is the circuit symbol of diode. This is the circuit symbol of diode, and the voltage across the diode is VD. This is small VD, and the current through the diode is ID. So in the on condition, when diode is conducting, when in the previous class we learned about this ideal diode model in which we approximate this curve as a straight as two perpendicular straight lines. Here you can see we have approximated this non-linear curve with a straight line and as we can see this value is zero point 0.7. This value is 0.7 volt, and you can see here that this is very near to the y-axis, and here we have approximated it like this, and we have approximated this very small current of order of microampere. So we have neglected that current, and we have approximated the characteristics like this, which is coinciding with the x-axis. So here our conclusion was like this id was equal to 0 when vd less than 0, and here the id is greater than 0. So in this modeling, what we are doing, we essentially we are doing this modeling on the basis of resistance. As we know, the IV characteristics of any electrical device. In previous lecture, we have already learned this. I am just recapitulating everything so that the continuity is not breaking for the modeling of diode, and then we will learn the next approximation, which is a better approximation, and the third one, which is the best approximation model. So in the ideal diode model, actually we have approximated on the basis of resistance. What you need to understand that if you are drawing some IV characteristics, and let us suppose the IV characteristics for a resistor, and if I draw a IV characteristics for a resistor, then the IV characteristics for a resistor is like this. The current increases linearly as we increase the voltage. We know that if the voltage across the resistor is increased, if we are applying the more voltage, then the current increases, as we know that I equal to V by R. So here the R comes into the picture, and with the help of this characteristics, how can we find the R? By the slope of this characteristics line. And here you can see if I try to find the R for an interval, let us suppose at there is some value of voltage is here at this point, and some value of voltage is at this point, and the corresponding current is here, and the corresponding voltage is here. Here you can see the change in current. So let us suppose this is I1, this is I2, and this is V1, this is V2. Here you can see the slope will be delta I by delta V. This I2 minus I1 over V2 minus V1. So this we know with the This we know by the basic coordinate geometry. So we can find the slope of this line. But what is the slope here? Slope is the inverse of the resistance. We can see the resistance is actually the resistance is V over I. We know that by the basic Ohm's law, the resistance is the change in current, change in voltage over change in current. And but the slope here is giving the inverse of the resistance. So this is the slope of this curve is 1 upon R. So here you can find the resistance. On the basis of this resistance, we have done this modeling. So when my diode is on, then this line, I need to represent this line. In modeling, actually we do not take all the attributes when we are modeling in engineering. If we are modeling in the engineering in basically in circuit analysis, then we need to model these characteristics with some known elements. As we know the open circuit, short circuit. We are familiar with these terms: open circuit, short circuit. So basically, we do not take all the attributes in the modeling. We take just some approximation. So here we have approximated. You can see here I have approximated this current value as 0, and I have approximated this 0.7 as 0. Okay, so we have done the approximation, and this is the first model, parallel diode model. And you can see the resistance here, and this I have already discussed in the previous class in the second way when we were discussing the second way of understanding the ideal diode model. So here if I try to find the resistance for this, if this line is like this, then what will happen? The resistance will be almost 0. You can see here the change in voltage is 0. Change in voltage is 0. And definitely there is some change in current. You can find change in current at any points. But when this line coincide with the y-axis, then change in voltage is 0. There is no change in voltage on the x-axis. So this delta I over delta V, this delta I over delta V for this delta I over delta V will be equal to infinity, which is inverse of resistance. Then R will be equal to 0, because the delta I over delta V equal to 1 upon R. So if resistance is 0, then we can represent it by just some wire, or you can say the short circuit. So this is how we represent the ideal diode model. When the circuit is conducting, when the diode is conducting, then we represent it like this. And when diode is not conducting, then we need to represent this region. In this region, you can see the diode is conducting, and in this region, the diode is non-conducting. Okay, so or you can say blocking. So if I need to represent diode in this region, now you need to understand diode is not a simple device like a resistor or like an inductor or like a capacitor, which are the linear devices. And why capacitor, resistor, and inductor are linear devices? Because they have the linear characteristics. You can see here. If I don't know if you have learned this thing in the network or some basic subjects like ECM, but you need to understand this. These three devices R, L, and C are the linear devices. Why? Because the IV characteristics of this resistor is linear, and capacitor, for capacitor, the QV characteristics is the linear. QV characteristics is the linear. You can see Q equal to CV. We know that QV characteristics is the linear characteristics for the capacitor. This will be a linear characteristic. And for the inductor, we know that phi equal to Li. The flux is there. So this phi and I characteristics is the linear. That is why these devices are linear. And we know that the different characteristics like I equal to C dV by dt. So we can obtain here I just by differentiating this thing, and we can obtain the voltage here just by differentiating this flux. We know that d phi by dt and d phi by dt, you have learned the Lenz's law. The flux is there. So the region of linear. Okay, ये अलग चीज हो गई. So let me come back to the point. The point was this: the on state. Now we were discussing off states. Now we will discuss off state. So when the diode is off, then we need to model this line. And in order to modeling this line, what is required? We need to find the resistance again. And if we try to find the resistance here, you can see here delta I is 0 and delta V, you can find that there could be any value between 2 points, but delta I is 0. There is no change in current in this line. So this 1 upon R is 0 because delta I is 0 and R is tending to infinity. So we need to model R is infinity. When the resistance is very high, then we can model it by the open circuit. Now, if you understood this modeling, then the remaining two modelings are very easy, which are dependent on this ideal diode model. We will use this ideal diode modeling in those modeling, and just one more element will be added. Just one more element will be added in those two modelings. And we solved some circuits in the previous class with the help of this modeling, and again we will solve the same circuits with the other kind of modeling. Okay, so now let us come to the second kind of modeling, which is the constant voltage source model, or you can say ideal diode model plus voltage source model plus constant voltage model. Okay, so let me clean this board. इस डायग्राम को रहने देते हैं, ये डायग्राम काम आएगा. Okay, the next model is constant ideal diode model plus constant voltage. और नहीं, there's a different nomenclature, बहुत अलग अलग है अलग अलग किताबों में, तो आप कंफ्यूज हो जाते हो. तो बस इसलिए मैं बिल्कुल बेसिक से चलूंगा. पहला मॉडल है हमारा आइडियल डायोड मॉडल प्लस volt. Second, first model is the ideal diode model, and the second model is the voltage source model. Ideal diode, ideal diode plus voltage source model. So this is a better model, because we are doing a better approximation here. So now we shall try to understand how can we do a better approximation than the previous one. So here you need to understand, if I shift this characteristics here, if I shift this characteristic, this is the characteristics here. If I shift this line here at this 0.7 volt, let us suppose I do it like this, then you can see this model is little better than previous model, because in the previous model I have neglected this 0.7 value, and here only I am neglecting this slope. Here in this model only I am neglecting this slope of this curve. You can see I am only neglecting the slope of curve. In the previous model I have neglected the slope as well as this constant 0.7 volt. But if I shift my model to the to some threshold value, which is a 0.7 volt for the silicon diode, 0.7 between 0.7 and 0.6, and for the germanium diode 0.3 to 0.35, and for the gallium arsenic diode the value is 1.2. so this threshold value is different for different diodes. Okay, so if I want to make some better model, then what can I do? I can represent here, I can shift this characteristics. So let me draw the diagram again with the shifted characteristics. So if I shift this characteristics little bit, then what? Then how can we do the modeling? So if I shift this characteristics, so here I have shifted the characteristics, and now I need to draw the axis here. This is 1 volt, 2 volt, 3 volt, 4 volt, and this is the VD, voltage across the diode, and or you can see the forward voltage drop on the diode. This is the ID, the current which is flowing inside the diode, and here this value, let us suppose this value